Hello all. In this lecture video, we are going to discuss about the chopper, different types of chopper. And first we will discuss about step-down chopper. So the contents in this unit is introduction to DC to DC converter, which is also called as DC chopper. The concept of duty ratio, and it is also called as duty cycle. We'll see the equivalent circuit for buck converter, the power circuit analysis and waveforms at steady state condition, and we will see the relationship between the duty ratio and the output voltage. There are some different control strategies where you can control the output voltages. So we'll see these two control strategies here, and we will see the one more converter called a boost converter. We will see how it is derived from the buck converter, and we'll draw the equivalent circuit. We analyze the circuit, right? Finally, we're going to derive the average output voltage and RMS output voltage. And at the last, one more converter, which is called buck boost converter, which is also called as step up, step down converter. Right? All these three converters we are going to discuss in this unit. Finally, we are going to solve some numerical problems on these three converters. Right? So let us see the definition of DC chopper. So as I told you, it is also called as a DC to DC converter. So the DC chopper is a static power transfer device or converter which converts the fixed DC input voltage to a variable DC voltage, right? And we'll see now how it is being converted to a variable DC here. So here we'll be having the power electronic converter. This power transfer converter consists of one main SCR and the commutation circuit. That is why the chopper is represented with a rectangular dotted box, and it is denoted by CH. The input to this chopper is a fixed DC, and the output we will get it as a variable DC, right? So the chopper means it is chopping the input voltage. That means it is cutting the input voltage into small pieces. So now we can see this kind of output voltage we may see across the load for a given input voltage. So input voltage, this the magnitude is always constant throughout its time period. It is a DC voltage. So out of this constant DC, we can get a variable DC across the load. So depending upon the on-time period and the off-time period, we can regulate the voltage across the load. Right. Now, there are some applications of this chopper. So wherever you require a variable DC, there you can use this DC chopper, but the input should be a constant DC or it may be variable DC. Right. For example, if you want to operate the battery operated vehicles where you need a DC to DC converter so that you can regulate the voltage, and obviously the variation in voltage will vary the speed of the battery vehicle. You can also use in subway cars, trolley buses, and speed control of DC drives. Right. You know that in case of in order to control the speed of a DC motor, there are two techniques, right? One is armature control, one more is a flux control, where we are going to control the armature voltage in case of armature voltage control, and in case of flux control or field control techniques, again we are going to vary the field voltage, or you can vary the field current with the help of the rheostat. Right, there you can make use of this DC chopper, and you can easily vary the voltage given to the field winding, so that the flux will vary and the speed of the DC machine can vary. Similarly, you can use in case of solar photovoltaic systems. You all know that solar photovoltaic system produces a variable DC because the output of the solar photovoltaic system depends on its weather condition, which is temperature and irradiation. so which is not a constant over the time. So those factor will vary. That means you will get a variable DC for a solar panel. So that variable DC can be connected to grid or DC grid, where you can make use of this DC chopper, where the DC chopper will convert the variable DC to a fixed DC, right? Similarly, you can use this DC chopper for a excitation for synchronous machine. So these are the few applications of this DC chopper. And if you see the concept of the duty ratio or duty cycle is defined as the ratio of the on-time period to the total chopping period, right? So this is the duty ratio or duty cycle, which is defined as the ratio of the on-time period to the total chopping period T. Right. So on the duty ratio, delta can be a maximum of 1. It can be maximum of 1. If T on equal to T, that means there is no on-time period, off-time period. So if you have complete on-time period, then T on will be equal to your total chopping period T. There you can get delta equal to 1. Right. And the minimum value of delta will be equal to 0. If there is no on time period, if you make the chopper always off, then I can say the T on equal to 0. If T on equal to 0, delta equal to 0, which means delta can be varied from 0 to a value of 1, maximum value of 1. Right, this is the variation of your delta, which is called a duty ratio or duty cycle. Now, there are a few techniques which are available where you can obtain the variable DC from either fixed AC or fixed DC. The first technique is called line commutated converters. These techniques we have discussed in second unit, which is called phase control rectifier, where we have converted the fixed AC to a variable DC. So it is converting the AC into a variable DC, right? So this is called line commutated converter. It is a single stage converter. Directly it is converting AC into the variable DC. And one more configuration is called AC link chopper, right? Means you will be having the inverter as well as rectification combination. It is a two-stage conversion configuration. Right now you can see the equivalent circuit here. It is converting the fixed DC to a variable DC in two stages. So first it is converting fixed DC into the AC with the help of the inverter. Then the AC which is there here, it is being converted into variable DC with the help of a rectifier. So it is a two-stage conversion. So you require two power types converter. The cost of the system will increase, space will increase, right? There is a reduction in the efficiency because more number of components you may use, right? So these are certain drawbacks. So in order to avoid these drawbacks, if you want to convert the fixed DC directly into variable DC, we are using a chopper, DC chopper. So let us see the equivalents, this DC chopper. Now you can see the DC chopper where it is called single stage conversion. It is directly converting a fixed DC to a variable DC with only one converter. And you can see this is only one converter. It is denoted by PEC, which means power electronic converter, and is represented with a rectangular dotted box, and chopper is always denoted with CH, right? So which means this box will be having the one main SCR. In addition to this SCR, will be having commutation circuit. So we know the SCR can be turned on with the help of gate terminal. So with the help of this gate terminal, we can make it on, right? So, but to make the SCR off, we can use the commutation circuit here. which is there inside this dog, right? So that is why this is, SCR is also called as a semi-controlled device. It is not a fully controlled device. We can make it on, but we cannot make it off with the help of gate terminal, right? So for this converter, we are going to apply a constant DC here, and this constant DC is being converted into variable DC here at the load side. Okay, so now you can see the output voltage, which will be a chopper kind of voltage. So you can see sometimes we may get voltage across the load, sometimes we will get zero voltage across the load, right? And the average output voltage will be somewhere here, right? So if you know the area under this curve, then you can calculate what is the average voltage across the load for a given duration, right? So this will be more efficient when compared to the previous AC link converter, AC link chopper, you can say. Okay, where we have used two converter. One will act as a rectifier, another will act as inverter, right? So here we are using only one converter, which is directly converting the DC into the variable DC and vice versa. You can also achieve the variable DC to constant DC here, right? So that means there are less number of components, only single stage conversion. So due to less number of components, the space will be less, right? And due to this reason, you can say the losses will be less. The losses will be less, you can get more efficiency, right? Let us see how we are going to get the variable DC out of the fixed DC, right? So now first we'll see the generalized circuit here. So this is the constant DC here, you can see. So our motto is to get a chopped kind of voltage across the load. Across this load, we need to get this kind of voltage. So sometimes the peak voltage, sometimes zero voltage. So this is our motto, right? So out of this DC, constant DC, I will draw the DC with the red color here. Okay, just above this line I want to draw so that you will get a clear cut idea. So this this red color represent your input voltage, right? So but I want to get the chopper kind of voltage across the load, right? To get chopper kind of voltage, let us consider a DPST switch here. Okay, and let us say this is what our power transfer converter, which is converting the fixed DC to a variable DC. Here we are going to apply the fixed DC, and across this load we can get the variable DC, right? Now when the switch is connected to position number 1, let us say it is a DPST switch, double pole through single throw switch, double pole. There are two poles here, pole 1 and pole 2, right? And a single throw you can see here. So when the DPST switch is connected at position number 1, now you can see here, so which is called on time period. So during on time period, the load is connected to a battery. They will be in parallel. So the load voltage will be same as the input voltage. That is why you can see some voltage across the load, right? Then if I want to get the zero voltage across the load, you can move the DPST switch to position number 2. If you move like this, then the load is completely isolated from the source, right? So, and you can see the load is short circuited by this wire. So you know the short circuit voltage equal to 0. So now you can see when the switch is at position number 2, you will get 0 voltage across the load. That is called T of time period. Similarly, to get some voltage across the load, move the DPST switch to position number 1, and to get 0 voltage, move to position number 2. Like that, you can achieve with the help of the mechanical switch, right? Now there are many drawbacks if you use mechanical switch. Now this mechanical switch is replaced by some power electronic switch or semiconductor switch. Let us see how we are replacing this mechanical switch with semiconductor switch. right? So this is our motto. We need to get this pulsating kind of voltage across the load or chopped kind of voltage across the load. So if you calculate the area under this curve, that will give the average value. So average will be somewhere here. You can see with dotted line here. This is the average output voltage across the load. Right. Now directly uh, now this is what the DPST switch. This is the DPST switch where the position number 1 is replaced with chopper, position number 2 is replaced with diode. So these two will behave like a switch here, right? Let us see how they are going to operate, right? And now you can see in addition to this DPST switch, which are now replaced with the chopper and the diode, the circuit is also having the LC. So these LC are called filter. So to reduce the current ripple, inductor is used. To reduce the voltage ripple, the capacitor is connected across the load. So this will behave like a filtering components, and they will filter out the harmonics which are there in the current as well as voltage, right? So now this is the equivalent circuit for step down chopper, right? Now when the chopper it is in and these are the equivalent circuit, expected waveforms for this buck chopper, or it is also called as step down chopper, right? So let us see. Now you can see here, as I told you in the previous slide, that this chopper is having one main SCR and the SCR is connected like this. So here anode is there, at this terminal cathode is there, and here you can see the gate. In addition to this SCR, main SCR, we are also having the commutation circuit that is there inside this block, and we are not bothering about that commutation circuit here. So the purpose of the commutation circuit is to make the chopper off. That is the main purpose of the commutation circuit, right? And you can make the chopper on with the help of this G terminal, right? So now before discussing the analysis part or before going to the waveforms, now let us see whether the SCR, the main SCR, it is in forward bias condition or not. Then only we can apply the triggering pulse to the gate terminal. So here anode is connected to positive, cathode may be connected to negative, to the diode or to the load. So the main SR it is in forward bias condition, which means the chopper it is in forward bias condition now. So now if the chopper is in forward bias condition, we can make the chopper on by applying the gate pulse. So let us say in mode 1, this is what mode 1, here to here. So during mode 1, we have applied triggering pulse to chopper because chopper it is in forward bias condition. So it is in on condition till this point. So during T on time period, the chopper it is in on condition, let us assume. So it is replaced by short circuit, right? And you can see the diode will get reverse bias because if you see the diode, it is connected like this. I will be having the diode in this fashion. So here at the moment you close the switch, this positive is connected to cathode of the diode, this negative is connected to anode of the diode, which means diode it is in reverse bias condition and the diode goes to off and is replaced by open circuit. So which means at the moment it is in on condition, you can see the direction of current, you can see with red color. It is flowing from VDC positive through chopper, inductor, through load and back to the VDC negative. This is the direction of current you can find. Okay, which means during this interval, the inductor is connected to the battery and inductor will charge and it will store the energy. So which means the inductor is carrying the charging current of the charging current. So you can see the output current, which is also called as inductor current, right? So the inductor current is now charging current of the inductor. And the diode, it is in off condition, you won't get any current to the diode. That is why you can see the diode current equals 0. Right? So diode current equals 0. And the chopper and inductor, they are connected in series. So the same charging current of the inductor is flowing through the chopper as well. So you can see the charging current of the chopper. Right? And due to presence of this current, you will be having some voltage across the load because it is having some resistance or some load. The current multiplied by the load impedance will be the load voltage. So you can see the voltage across load will be something here. Right? So just these are the equivalent circuit during mode 1. It is from 0 to t on. So this time duration is from where t, this is a time axis t, which is you can see that t is greater than 0, but it should be less than t on. Right. Similarly, if you want to go for mode 2, so in mode 2, we want to make the chopper off. To make the chopper off, we need to make use of the commutation circuit. Right? So it may be class A commutation, class B, class C, class D, or class E commutation. We are not bothering about the circuit configuration for the commutation circuit. So here the mode of the commutation is to make the chopper off. So now if the chopper is in off condition, you can see like this, it is replaced by open circuit. Right? Now previously the inductor is charged to some extent. Now the inductor has to discharge. So before discharging the energy which is there inside the inductor, it has to replace its polarity. So the minus polarity is replaced by positive here. And this positive polarity is being replaced with the negative. And the inductor will start discharging. So if you see, at the moment the chopper goes to off condition, diode will become a forward bias condition because this negative polarity of the inductor is connected to the cathode and this positive may be connected to the anode of the diode. So diode will be in forward bias condition, it will conduct and it will carry the current. Right? So now the diode is carrying discharging current of the inductor and you can see the current is leaving from the positive terminal. So for this loop, the source is the inductor. So the current is leaving from L positive to load through diode anode cathode and L negative. So this is the direction of current which is flowing in this path. That is due to the presence of the energy stored in the inductor. So inductor current is also, you can see it is a output current. So it is a discharging current, right? And the discharging current is flowing through the diode as well because they connected in series now. So diode is suddenly goes to maximum value and then it will carry the discharging current of the inductor. Now if you see the current through the chopper is in off condition because we make it as off with the help of the commutation circuit. So it won't carry any current, so the chopper current equals 0. Now this load is short circuited by this diode. So the short circuit voltage will be 0. So you can find the voltage across the load equals 0. So this is during the off time period, right? So these are the equivalent circuit and the corresponding waveforms. So now if you know the waveforms, now you can easily apply mathematics and we will try to find out what is the area under this particular curve, right? So to derive the average output voltage, you just take the integral. So take the, this is for one complete cycle, one chopping cycle you can say. So I can write to calculate area under this one cycle, I can take 1 by T, the total chopping period, and 0 to 2 into VDC, right? But the output voltage we can see only from 0 to TR, 0 to TR, right? That is why now the integration is from 0 to TR into VDC. You just integrate this VDC, which is constant one. So it will be T, and the limits are 0 to TR. And if you substitute the upper limit, T on minus 0, directly write T on by T into VDC. So this T on by T, you can write it as a delta. Delta is the duty cycle. Okay. And if you want to write in terms of chopping frequency, then 1 by T, you can write it as F here, chopping frequency F. So the average output voltage will be F into TR into VDC, right? Where F is the chopping frequency and delta is the duty cycle or duty ratio, which is defined as the ratio of the on-time period to the total chopping period. Similarly, we can derive the RMS output voltage for this buck chopper or step-down chopper. You just do the root for the root mean square. So now it is root mean means 1 by T, this total chopping period, squaring the input voltage. So limits are 0 to T into VDC square, right? And you can see the waveform where we can get the voltage across the load only from 0 to TR. That is why the limits are from 0 to TR, right? And you can take the VDC out of the root, the square root will get cancelled. You can write VDC under root of 1 by T, integration from 0 to TR into 1 into dt. And the integration of this one will be T. You just substitute the upper limit as lower limit, and you will get it. You will get the RMS output voltage as this VDC into under root delta, where delta is the duty cycle, right? Which is given by T and by T. So there is this is one method, method one. You can also achieve the average output voltage with the help of one more method, right? So this is method two. Now same expression when the chopper is in on condition is the equivalent circuit. Just now we have discussed about the circuit. When the chopper is in off condition, this is the equivalent circuit. Okay. Now only thing is that you just apply KVL in this loop, so it will be minus VDC. Remember that these analysis we are doing for assuming the diode and the chopper, they are ideal one. So we are not consider the voltage across the chopper and the voltage across the diode during on condition, which means they are in ideal condition. So I can write minus VDC. There is no drop across it because ideal switch plus VL voltage across inductor plus V naught that equals 0. So now from this one you can write voltage across inductor equal this much, VDC minus V naught. Similarly, in second case, you can apply KVL in this loop. So and you will get the voltage across inductor is minus V naught, right? And in steady state condition, the average voltage across the inductor should be 0. Why? Because if you want to see the voltage across the inductor, and that will be something like this. So you can see the voltage across inductor will be when the chopper it is in on condition, you will get positive voltage. When the chopper it is in on off condition, you will get negative voltage, positive, negative like this. So now at steady state condition, this area, the area during on condition will be same as the area during off condition, right? So or you can say volt second balance principle. So the time multiplied by this voltage, that should be equal to this time duration multiplied by this area will give the if you make it equal, then you will get area under this curve will get cancelled and you will get the average voltage across the inductor will be equal to 0, right? So the same thing we are doing here. In steady state condition, the average voltage across the inductor is equal to 0. So therefore you can write VL that equals 0. So now we have seen During on condition, the voltage across inductor is VDC minus V naught. During off condition, the voltage across inductor is minus V naught, and that we are making it as 0. Since T is the summation of T on plus T off, so from this you can write it as T off equal to T minus T on. So instead of T off, just substitute T minus T on, right? Divide this above equation by T, then you can write T on by T into VDC minus V naught, and this factor by T into minus V naught, that equals 0. So we know that T on by T is the duty ratio, duty cycle. So T by T you will get 1. T on by T again it is duty ratio, right? So if you see here, right? So now you can see this factor, this will get cancelled. Minus delta V naught plus delta V naught will get cancelled. So you can see delta VDC equal to minus VDC, that equals 0. Right. So from this equation, you can say the average output voltage across the load equal to delta times VDC, where delta is the on time period to the total chopping period. So the same expression you can see which you have derived in the method 1. Right. So this is about the method 2, which is a very easy method. Right. Now we can solve some problems, 2-3 problems based on this buck chopper. So this is a problem number 1. For the buck chopper, the input voltage he has given as 30 volts. The load resistance he has given it as 50 ohms. Duty cycle also he has given 50%, which is 0.5. Now he has asked to calculate what is the average output voltage, average output current, RMS output voltage, output current at the instant of commutation. Right? So these things we need to calculate. Now just now we have derived the expression for the output voltage, right? So these are the given parameters. We know that the average output voltage equal to delta times VDC. So delta he has given it is 50%, 0.5 into the VDC is 30, that will give the average output voltage as 15 volts. Average output voltage by the load resistance will give the average output current. You can find it as 0.3 amps. Similarly, we have derived the expression for RMS output voltage, which is root 2 delta times VDC, where delta is the duty cycle, which is 0.5, root 0.5 into 30. That will give it as 21.21 volts is the RMS output voltage. And the output current, the instant of commutation, at the moment you commutate the chopper, you will get the voltage across load as 30. So 30 volts divided by 50 ohms will give the current. So this is the current, the moment of commutation, right? So similarly, we'll solve one more problem. We'll go through one more problem, right? So this is the one more problem you can find. Now it is also step-down chopper. He has given the load resistance of 20 ohm. Input voltage as 220. When the chopper remains in on condition, voltage across chopper is 1.5 volts. So the chopper is not ideal one. Now it is a practical one. It is having some voltage across it. The chopping frequency is 10 kilohertz. Duty cycle he has given 80%, which is 0.8. And he has asked to calculate the average output voltage, RMS output voltage, and the chopper efficiency. Right. Now, when the chopper it is in ideal one, voltage across chopper equal to 0. Right. If the chopper is ideal one, you can say blindly the chopper efficiency is 100%. Right. But due to presence of some voltage drop across the chopper, which is of 1.5 volts, you cannot get 100% chopper efficiency. Now we'll see. So these are the parameters. Now we have derived the average output voltage and RMS output voltage considering the chopper is ideal one. There is no voltage drop, right? But if there is some voltage drop, because if you consider practical one, now the expression for the average output voltage will be delta times VDC minus VCH, right? If it is ideal one, no need to consider this VCH, it is delta times VDC. Just now we have seen those expression, right? So now you just substitute V chopper, VDC, which is 220, and you will get the average output voltage is this much. Similarly, you can write the expression for RMS output voltage, which is root delta times VDC minus VCH. Now substitute VCH equal 1.5, VDC is 220 volts, and delta is 0.8. So we'll get it as 195.43 volts as the RMS output voltage. Now to calculate the chopper efficiency, uh, we need to consider what is the output power of the chopper and what is the input power to the chopper. Now output power of the chopper is output current multiplied by output uh, voltage. In terms of voltage and resistance, you can write the output RMS current will be V naught RMS by R, right? And if you substitute here in place of this I, it will be V naught RMS square divided by R, because the known factors are RMS output voltage and the load resistance. So we are converting the unknown factor to the known factors. Now, if you consider the chopper drop, and this is the output power, right? Because V naught RMS equal to just right square of this one means square root will get cancelled. You can write VDC minus VCH whole square divided by R, right? So this is the P naught output. So you just substitute alpha, VDC, and VCH, and you will get the output power is this much, right? Similarly, the input power is given by this expression, and you substitute all those factors, parameters, you will get the input power is this much. So this output power divided by the input power, which is 1922.8, this will give the chopper efficiency as 99.318 percentile, right? So let us say, as I told you, if there is no drop across the chopper, considering the chopper is ideal one, we should get 100% efficiency. Let me cross check that one, whether we are getting 100% or not. Now, if there is no drop, the chopper voltage equals 0. That means it is alpha into VDC square divided by R. And here also you can see, if there is no voltage drop, you can remove this V chopper. Then it is alpha into VDC, which is VDC square divided by R. So same as the previous one. So we will get the output power is alpha times VDC square by R. The input power is also alpha times VD square by R. That means numerator denominator will get cancelled. You will get 1, which is 100%. Right? So this is all about buck chopper. Now in the next class, we'll discuss about boost chopper. Thank you.